And welcome back, everyone. Welcome back to chemistry. I'm excited for class today because today we get to tie a bunch of ideas together. We get to look at this Schrodinger equation and see that the solutions to this equation give us a wave function that's going to describe the shape of an orbital. If we square that wave function, we get the probability of finding an electron somewhere in that region. The solution also gives us the energy of that orbital. And we're going to see we have a whole variety of orbitals to choose from. S, P, D, F, different principal quantum numbers, different orientations of these orbitals. And we can learn about their shape, the probability of finding an electron there, and its energy. And we can convey the solutions of Schrödinger's equation. We can convey these wave functions in a variety of different ways. And we need to understand how to work with these different types of ways of communicating about orbitals. The wave function applies to an orbital. It tells us something about that. So that's why we have this symbol here. That little psi function is the wave function. But then in the subscript, we tell you what orbital we're talking about. So maybe it's a 2s orbital. That means the principal quantum number is 2 and the L quantum number is 0. So we could say it's a 2s. Or we can use the notation, again with that psi symbol, where we give the first quantum number, the principal quantum number, the next one, that L, and then a magnetic quantum number, the third quantum number. We can use both of these symbols to talk about the wave function, which is just talking about the orbital. And we've learned that for different principal quantum numbers, we have different options for relevant orbitals. So if the principal quantum number is 2, right away we know that orbital is going to have one node. If the principal quantum number is 2, well, L could be 0 or it could be 1. So that means we could have a 2s orbital or we could talk about 2p orbitals. On this slide, we're talking about 2s orbitals. The ML option for the 2s orbital is just 0. There's only one way to have a 2s orbital. The 2s orbital is very similar to the 1s orbital, except it's bigger. It's still a sphere, kind of just like a ball, but it's larger and it has one node. So I brought, here is my, let's try this again. Here's my nice little squishy ball from Dollarama. That would be representative of my 1s orbital. Well, then I have another squishy ball here. Here is my 2s orbital. Imagine that it's bigger, has a higher principal quantum number. But if I sliced it in half, it reveals a set-in different phase inside. It's kind of like those nesting dolls. If you cut it in half, which I actually did with a knife, you can see that it has a different phase on the inside. Now, if I sliced this right here, we can see that the blue turns into pink and the pink turns into blue, or positive phase turns into negative phase and negative phase turns into positive phase. But this is really where the two phases meet is the node. This is one spherical node. It looks like a circle right here, but we can see it's actually 3 dimensions. It crosses at this positive negative phase barrier and passes at this positive negative phase barrier, but it is one node. So right here on the figure A, the top one, we're plotting out the wave function. Here we're only showing it in 1 dimension. My ball over here is in 3 dimensions. Drawing that is a little bit more tricky. So for this graph here, it's only in 1 dimension, just along the x-axis. We can see the positive phase becomes negative phase as we move away from the nucleus. So let's imagine the nucleus is right here. As we go out from that, it goes from positive phase and crosses into negative phase. Where that change happens, that's a node. The 2s orbital has one node. As we go out from the center one way, we have a node. As we go out from the center the other way, we have a node, but it's the same node because this is a spherical node. That's the one-dimensional picture. The bottom left is the three-dimensional picture. We call this the isosurface. Gives us an idea of the shape and the size. We can't see inside this ball. That's why I brought my squishy ball over here so that I could open it up and show you what's inside. Inside of that isosurface, there's a different phase inside. I can take the square of this psi function, which is what I'm going to do over here. Now, you know when we square something, the positive value stays positive. A negative value turns into a positive value when we multiply negative times negative. And now we're at a probability density plot. So that means at the top, we're looking at higher probability. And right here is 0 probability. Closest to the center where the nucleus is, the electrons closer are hanging out closer to the nucleus. As we go out farther, we're less likely to find them there. And we can see that we cross the 0 line here again. So that is where the node is, and it's a spherical node. So we can see high probability, low probability. As we go out on the edges here, it just kind of hovers. So it doesn't actually cross the 0 line again for 0 probability. It just gets lower and lower and lower, so less chance. Then we go to the bottom right. We have the square function again, so we're looking at the probability. But now it's a 3D image, but I've taken a slice of this 3D image. So I've taken my squishy ball that has a nested ball inside. I've cut it in half, and I've given you a picture taken with a long exposure camera, and every dot is telling you that the electron was there. So the first second, third second, fourth, fifth, 10th, 10,000th, 1 millionth, and you can see where the electron was. Usually it's closer to the center. You can see it has a circular shape. This is a slice, so in 3 dimensions it's spherical. And we can see a region where there aren't any green dots. That region is the node. We're not going to find electrons in that nodal sphere. Okay, so we've talked about the 2s orbital when L equals 0. We're now going to advance what happens if L equals 1. The principal quantum number is still 2, but now the next quantum number is 1. That tells us we're looking at 2p orbitals. Well, the third quantum number, that magnetic quantum number, ML, can go from negative L to positive L. Since L is now 1, that means ML could be negative 1 or 0 or positive 1, which tells us we have 3 orbitals that are 2p orbitals. We can plot out, we'll start with the top left, the wave function of a 2p orbital. We're going to look in 1 dimension. I'm just going to look along the x-axis to keep it nice and simple to start. I can see I have a positive phase, not charge, but just phase, like the up part of a wave, and the negative phase. Where the negative phase and positive phase cross, that right here is our node. Since we're still at principal quantum number 2, 2 minus 1 is 1, we have one node that we're expecting to find. I can take that psi function and I can square it as I go to my electron probability density map. This gives me an idea of what's the probability of finding an electron somewhere along this x-axis. I'm still just in a one-dimensional region right now. We can see most often we're going to find it about this far from the nucleus, less likely closer to the nucleus, less likely further away, most likely somewhere on either side of the nucleus. And we could take a 3D cross section, so like a little slice, and see if we took that long exposure camera, the electron is often somewhere there, and we kind of have this dumbbell type shape. I'm going to go back up to my psi function, my psi 2p orbitals, and now I want to look at it in 3 dimensions. I want to look at the isosurface, look at the 3D view visualization of what this wave function looks like. We know there are 3 orientations, -1, 0, and 1. I don't know which is which, but there's one of each. We have a positive phase and a negative phase. Now I brought a red and blue balloon that are kind of looking like those p orbitals. Now orbitals are not balloons. The electron doesn't live inside the balloon. We can see probably, most probably, it's hanging around somewhere here, but maybe once in a while it's going to be out here. Maybe once in a while it's going to be over here. But this gives a general likelihood of where it might be. This gives the general shape as the wave function. We square it and we get the probability of finding it there. So we have 3 orientations. The first is the px orbital. So I'm going to say my arm is the x-axis and the px orbital lies directly along the x-axis. The py orbital lies along the y-axis, so straight up and down. And then the pz orbital lies along the z-axis pointing straight towards you. All of these exist at the same time. If we have electrons in them, there could be some in px, 2 electrons there, some in py, 2 electrons here, and some in pz, 2 electrons here. This is why we have 3 options for the 2 p orbitals. One is along the x-axis, one along the y, and one directly along the z. Now we call these 3 orbitals degenerate, which means they have the same energy. Take your pick, px, py, pz, but they have the same energy. Okay, so question for you, where are these nodes in the 2py, x, and z orbitals? So first, let's look at it with the balloons, and then we're going to draw it on our paper. So when we're looking at the 2px orbital, these lobes, even though they're not balloons, but it's a nice visualization, these lobes lie directly along the x-axis if we're talking about the 2px orbital. The node is a nodal plane, and it lies right between these 2 lobes. So this time it isn't a sphere like the S, it's a plane. If I'm looking at the py orbital, it's going to be this plane here, again, lying in this region. And if I'm looking at the 2pz, pointing it towards you, it's this plane right here. I have one more visualization to do, and then we're going to draw this on our paper. So I brought my Easter eggs with some magnets. Here, this is lying along the x-axis. The yz axis is the plane. My py, my xz axis is the plane. And my pz, when it's pointing towards you, here's the plane cutting right through where we're never going to find an electron along that plane. Okay, so now the trick comes in. How do we draw this on a 2D screen and in your 2D notebook? Well, the 2px is lying along the x-axis, so it's the yz plane that is the node. So it doesn't intersect with either of those lobes. If we're looking at the 2py orbital, it lies directly along the y-axis, which means now the xz plane is the nodal plane that lies right between those lobes. And when we're looking at the 2pz, it's the xy plane that is the nodal plane. And again, it's easier if we have some three-dimensional objects to play with. One more final visualization. Here's my Z and the plane where no electron is going to be found. Thumbs up if this makes sense. You're able to visualize this. Awesome. Okay, let's keep jumping along. Ooh, we'll label our planes first. So what do we have here? X, Z, and X, Y plane. Okay, super. So we've been learning about the principal quantum numbers. We've done the 1 options. That was the 1s orbital. The 2 options, 2s and 2p. And now we're getting to the principal quantum number 3 options. And as you can guess, we're going to have s, p, and d. So if L equals 0, that means we're talking about the s orbital. If L equals 1, we're talking about the p. And if L equals 2, we're talking about the d orbitals, and we haven't done d's yet, which is what we're going to focus on now. Since the principal quantum number is 3, 3 minus 1 is 2, we're expecting to find 2 nodes in each of these orbitals, and they're going to look differently. So let's start with the 3s. Now here in your workbook, we don't actually give you the plot of the psi function and the density plot. They get a little bit more complicated, a little bit more interesting, but you probably have an idea of what the 3s orbital is going to look like. The 1s was a small sphere, 2s was a bigger sphere, 3s an even bigger sphere. But this time, the 3s orbital has 2 spherical nodes inside of it. So you don't have a visualization of this, but you do in your team module. So in your Topic 2.1 team module, we give you links to different websites that allow you to play with different activities, different visualizations, different plots of orbitals. So here we have a 1s orbital. We're looking at the probability density plot, and we're just looking at a slice of it. That's why it's flat, even though it's rotating. When we go up to the 2s, that white region between the blue and the red is the node. And now we're at 3s, and we can see the phase has changed again. And now we have 2 nodes, a smaller sphere and a larger sphere where we're not going to find those electrons. Okay, so 3s is taken care of. 3p is going to look very similar to the 2p orbitals. The 3p orbitals also have a nodal plane between the 2 lobes, but it also has like some type of spherical node right here that makes them look a little funky. So we don't actually give you a picture of this one, but it's still a dumbbell shape and it has 2 nodes. The 2p orbitals are small dumbbells. The 3p orbitals are bigger dumbbells. The 4p orbitals even bigger, but keeping the same shape. Where we want to focus now are the d orbitals. This is when L equals 2. We know we're talking about d orbitals. Now, if L equals 2, then the third quantum number could be -2, -1, 0, +1, and +2, which tells us there are 5 possible orientations of the d orbitals. These are also degenerate, which means they have the same energy level and we're talking about an isolated atom all by itself. We're going to see as we move along that it actually gets a little bit more interesting. But when it's all by itself, these are degenerate. Okay, so let's see if we can visualize the d orbitals. Now we have one orbital. Let's start with the one on the top left, the 3d xy orbital. Now this one, the subscript there tells you the plane that the lobes lie on. So now this is a 3D orbital. It has 4 lobes, but this makes up one orbital. The 3D xy orbital, that subscript, tells you that it lies along the xy plane. So if I have my flat piece of paper, I'm going to try to align it like you have in your workbook. This is the xy plane. Notice that the lobes, these 4, they're not balloons, but we can visualize it with balloons, they lie between the axes. So notice that it's not pointing directly along the axes like the px, py, pz. Those were directly along the axes. Now it's between the axes, but it's on the x minus z squared. I'm going to do the xy. It's lying along the xy plane. X squared minus y squared means we just rotate it. I think that's 45 degrees, so that the lobes lie directly along the x and y planes. So now see how they're pointing directly there. Okay, so I'm going to hold this up. The xy plane I'm saying now is straight up and down so you can see the change. xy would lie between the x-axis and the y-axis. X squared minus y squared, it lies along the axes. Just that shift. Okay, the final one is the dz squared. And this is the kind of funky one because it looks like it has a donut happening. So imagine, let's see if we can align this. We still have the blue lobes going up and down, but now my red balloons have turned into like one of those inner tube donuts. Does anyone like to swim in those things where you have like it around your waist and you can flutter around? So it kind of looks like that, but the red balloons have turned into a little belly donut. And that's where we get our dz squared. The name comes because it's lying now. The blue lobe is lying along the z-axis. Okay, why do we have 4 that look very similar and one that just kind of looks funky? Well, when we look at the probability density plots, that long exposure camera where we're capturing where the electrons are hanging out, I have the one for the xz plane. So let's imagine that I'm holding this along the xz. So now I'm saying z is straight up and down, and the x, where's x? Pointing out towards you to the left. We can see, based on the probability density plot, that the electrons are mostly hanging out in these 4 lobes, which makes one orbital. It has 2 nodes. It has 2 nodal planes. So here, we can see one nodal plane lies straight up and down, the way that I'm holding it. And the other nodal plane lies straight side to side, based on how I'm holding it. Hopefully we can see those. The dz squared, this is the funky one that looks like the donut. But the cool thing is, if you look at its probability density map, that's on the bottom right corner, it looks awfully like the dxz. If we cut these nodes, now it's kind of like a cone. So I take this paper and I wrap it up like an ice cream cone, and it wraps around the bottom and the top, kind of like a cone like this. So we have one up cone and one down cone. That's our node. And we get a cross section of that probability function that looks a lot like the other ones. So they're very similar. We have 5 degenerate orbitals, and they are the 5D options. Okay, so I think it's important to realize that all of these orbitals for an atom that has enough electrons to have electrons that are in these orbitals, or that have these wave functions, they're all existing at the same time. So let's see what it looks like when we overlay the orbitals we've talked about thus far. The music is just incredible. I mean, you can't beat the music. Orbitals. So here is our s orbital, our sphere. Then we have our px along the x-axis, y along the y-axis, pz directly along the z-axis. Then along the z plane, that's the first D option. Along the y plane, notice it's not pointing at the axes. Along the YZ plane, and then directly on the XY plane, but right on the XY axis, and then our cool donut one along the Z axis with that inner tube. And they're all hanging out at the same time. Okay, so that gives us an idea of where these electrons are hanging out in our atom. Okay, thumbs up if you're following so far. We've identified the shapes, we've identified the nodes. Okay, let's continue along. Oh, we have this exercise first. Let's do this. Okay, let's wrap up the ideas that we're talking about and do an example. So we want to write the wave function symbols, that's this, when n equals 3, right here. And we're going to use the nomenclature using the first 3 quantum numbers. Then we want to identify which one is 3s, 3p, and 3d. So let's start where all of these are going to be n equals 3. That's our principal quantum number. Then we're going to have the 3 L options. We start with L equals 0. L could be 1, or L could be 2. Remember the quantum number rules? L can go all the way up to n minus 1. L is not allowed to equal 3 when n equals 3. So if L equals 0, well, then the ML option could be -0 to +0, which is basically just 0. So the wave function that we have using the NL, ML nomenclature is 3, 0, 0. That's the way that we can talk about this orbital, and that means we're talking about the 3s orbital. If L equals 1, well, the ML options are -1, or 0, or +1, which means the functions that we're talking about, the wave functions, are 3, 1, -1, 3, 1, 0, and 3, 1, +1. These correspond to 3p orbitals. There's a 3px, a 3py, and a 3pz. I don't know which one is which, but we know that 3 exist, and this is how we can classify them. If L equals 2, well, the ML options are -2, -1, 0, +1, and +2. So the 5 psi options showing the d orbitals are 3, 2, and I'll just write them down. And what are those 5 options? Well, you can go back a page and identify what those are. Okay, so I'm going to leave this up on one screen because I have a clicker question for you today. Which label could correspond to this orbital? Chat with the person beside you and submit your answer. And 10 more seconds. And 3, 2, and 1. Okay, most people went for E, followed up very closely by D, because D and B are correct. And 3, 2, and 1. Okay, so most people chose D because it definitely looks like the one that we just introduced to you, the dz squared. Absolutely. When we use the other nomenclature though, n equals 3, L equals 2, that's one of the options. Sorry, no, L equals 2 tells us that we're talking about the d orbital. The 0 could be -2, -1, 0, +1, or +2. As long as it's one of the options, it means we're talking about a 3D orbital. How could we rule out A? Who can just shout it out? Why is A wrong? Yes. Because it's a 2, that's right. 2D orbitals don't exist. D only starts at principal quantum number 3. And that's telling us it's the XY plane. So multiple things wrong. Why is it not a PZ orbital? Anybody want to say? There we go. It's not the same shape. The lobe is the same. It's along the z-axis, but it doesn't have the donut. So that's why the P is incorrect. Okay, well done. Yes, question.
Well, I wonder for the B question is 3 to 0. You didn't identify like the 0 is the same. I mean.
That's correct. So I can't conclusively look at option B, the 320, and say that is the dz squared. I don't know. But the question says, could it correspond? If it said which one is the only correct, well, then you could go for the dz squared. But the 320 could be telling you about the d orbital. It's one of the options. Yes?
It's fast because with the point of we don't know which one it is, how do we know which one to answer? Because from my perspective, when I was answering, I was like, we don't know which one it is, so therefore I can't know if it's not the most effective answer, and the most effective answer is B.
Okay, great question. So the question is, if this was on a test, how could this be fair, basically? You said it much nicer than that, but I'm just going to be blunt and say, how is this fair? It's definitely a dz squared, and I agree with you. It is a dz squared. I don't think this would make an excellent exam question. But because we can talk about the nuance of it, it makes for a discussion question. During an exam, yes, you usually have to choose the best answer. So the best, I would agree, is dz squared. That said, E is also an option. And the question says, which label could correspond to this orbital? It doesn't say which one defines it most accurately. That would be the dz squared. That gives you the most information. But could 320 be referring to a dz squared? Yeah, it could. So that's where we have option E as the best answer here. For an exam question, it should be very clear. But for exam questions, sometimes there are multiple multiples. Sometimes B and D could be correct, so then you do need to choose the one that includes more. Exam questions, it will be very clear, correct and incorrect. This one is more of a discussion question. Great question. Is that better? Okay. Okay, so we're tying it in together now. We know how to visualize these orbitals, look at their shapes, but now we want to do something more useful with it and figure out where the electrons are in these atoms. So we've looked at 1s, 2s, 2p, 3s, 3p, 3d, and we know that the list keeps going. Now, originally, we said the principal quantum number, 1, 2, 3, tells us about the energy of the orbital. And that is true, but figuring out which specific orbital, a 2s versus a 2p, gives us a little bit more information about that energy. It is true that 2s has a greater energy. Energy is increasing along the y-axis here. 2s has greater energy than the 1s. We know it's bigger and has higher energy. And the 3s even greater, and the 4s and the 5s. The energy definitely increases as the principal quantum number increases. That is true. We can look at the same pattern when we're looking at the p orbitals. 3p has greater energy than 2, and it keeps increasing as the principal quantum number increases. That is also true. Another pattern that we can draw from here is that as we go from S to P to D to F, if the principal quantum number is constant, SPDF, as we move along, the energy increases. So those are patterns that hold true. But we have electron repulsion happening when orbitals of the same principal quantum number are existing at the same time. So 2s and 2p, they start to repel, and it results in a slightly different energy level between the 2s and the 2p, and the 3p, and the 3d. And they can differ so much that the patterns that we want to follow all the time start to become a little bit smudgy. It starts to overlap, and we have to pay greater attention because sometimes the overlapping means that the highest principal quantum number may or may not have the highest energy. So how do we know where the electrons are? Well, they're always going to exist in the lowest level energy orbitals. That is until we zap them with voltage or we fry them with photons and they get excited. But we're going to talk about ground level electron configurations. When the electrons are in the lowest possible energy state, that's how they usually exist. That's the rules that we're going to talk about. So if we're trying to figure out where the electrons are, what orbitals we can use for them, we need to fill the lowest energy orbitals first. And this has a name, it's called the Aufbau principle. But how do we know which orbitals to fill first when they start to overlap at the top? For example, as we walk across, so 1s to 2s, sure, we knew that. 2p, sure. 3s, 3p, 4s, 3d, 4p. All of a sudden we have to start zigzagging through these different orbital energy levels. How can we figure out the order to fill? Well, we have an amazing strategy using our periodic table. There are different strategies for remembering how the energy levels of these orbitals exist. And I'm really excited to show you how to use your periodic table. This might be review for some of you, and it might be new for some of you. I'm excited to tell you that you will always have access to a periodic table when you're writing tests and exams in first year chemistry. The periodic table that you will be given for tests and exams is the same as the one on the back cover of your workbook. So if you flip over, I think that's my next slide. There you go. That's the one that you're going to have access to. So you want to learn how to use this to solve as many problems and glean as much information as possible from this. Okay, and 3, 2, and 1. Thanks. When we look at our periodic table, we can get more than just the symbols of the elements. We can get more than just the masses. Based on where the element is located, it also gives us information about which orbitals the electrons are hanging out in. On the left-hand side of your periodic table, we call this the S block. Helium, we kind of imagine over there. Then we have our P block, our D block, and our F block. When we're placing electrons and figuring out electron configurations for atoms, we always start at the top left of our periodic table. How many electrons can fit in one orbital? Show me with your fingers. 2, that's right. How big is the S block? 1, 2 elements wide. The alkali and alkaline earth metals are our S block. How many electrons can we fit in the 1s orbital? 2. How many electrons can we fit in the 2s orbital? And the 3s orbital? Yes, this gets boring. So let's jump over to the P. We know there's Px, Py, and Pz. There are 3 degenerate, same energy level, orbitals for 2p, 2px, 2py, 2pz. Each of these orbitals can hold 2 electrons. How many total electrons can exist in 2p orbitals? Show me with your fingers. 6, that's right. 1, 2, 3, 4, 5, 6. Great. Want to guess how many can fit in the 3p set of orbitals? Show me with your fingers. 6, there we go. 1, 2, 3, 4, 5, 6. All the way down the P block, there's Px, Py, Pz. Basically take the number of columns divided by 2, and that tells you how many p orbitals there are. Show me with your fingers. How many d orbitals did we learn about today? How many 3d orbitals are there? 5, that's right. Each one fits 2 electrons. That counts to 10. Want to guess how big the d block is? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We didn't talk about the f orbitals. If we did, guess how many 4f orbitals there are. Show me with your fingers, or quickly count the lanthanides and actinides. 7. That's right. If we counted across the 4f block, there are 14 elements there. Divide by 2, 2 electrons in each f orbital. There are 7 f orbitals. This is a great way to double check your work because you know where they are. Next cool thing to glean from learning how to use your periodic table. S starts at 1. P starts at 2. D starts at 3. F starts at 4. Is there a 1p orbital? No, it doesn't exist. See that big empty spot? Is there a 2d orbital? No, it starts at 3d. So if you write 2d, something went wrong. The quantum number rules align with our periodic table. We have discovered all of the elements we're going to discover. We don't have any holes here. There were cool discoveries happening when scientists were building the periodic table and trying different ways to organize the elements that we knew of. When they started arranging it in different ways, there were gaps. There were holes. They were doing it by molecular mass, molar mass at the time. Based on holes, they were able to look for and find new elements that they didn't know existed before. We now have this beautiful set. Yeah, we still have some synthetic stuff happening at the bottom, but for naturally occurring elements, we're pretty confident we have them all. Using our periodic table, we can figure out the electron configurations. So this is the periodic table that you're going to have. You don't have this in your notes, but you do have this on the back cover of your workbook. If you want to sketch a quick periodic table, when I am doing my chemistry homework, or at least back when I did, or when I sit down for an exam, I label S, P, D, F, and then on my periodic table, the paper version I'm given, S starts at 1, P starts at 2, D starts at 3, 4 starts at F. And then we can use this to write out our electron configurations. For example, we're just going to talk through this one. For oxygen, if I wanted to write out its electron configuration, I'm going to do it right here. So we're going to do this example just quickly to begin. Oxygen, I want to write out the electron configuration for oxygen. I'm going to start at the top left of my periodic table, which means I'm starting with a 1s orbital. I count across. 1, I'm going to imagine helium is there. 2, I fit 2 electrons there. Is there a 1p? Nope, it's just kind of a big blank column. So then I jump down to 2, which means I'm still in the s block. I'm talking about a 2s orbital. I count across. Lithium and beryllium, kind of counting spaces. 2 electrons can go in the 2p orbital. Then I jump over to my p block. Is it 1p, 2p, or 3p? Well, I've labeled my periodic table, so I know I'm starting with 2p. How many electrons to get to oxygen? 1, 2, 3, 4. 2p, 4. We can use our rules, our quantum number rules. You might have different tricks for filling and writing out electron configurations, but learning how to use your periodic table comes in really handy because you always have your periodic table. That's where we're going to wrap it up today. We'll look at more interesting electron configurations next class. Have a great week.
Alright.